Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. In this video lecture, we are learning how to find the inverse Laplace transformation by partial fraction. So this is our third method for finding the inverse Laplace transformation. So actually friends, this is the second lecture which is based on this partial fraction concept. In our previous video lecture, we learned how to find the inverse Laplace transformation by partial fraction, where we cover some simple example where we get answer in straightforward manner. Now in this video lecture, we are going to cover such type of example which is somehow critical for solving the example based on the partial fraction. Now let's take the first example. So example is, so evaluate. So first example is evaluate inverse Laplace transform of, suppose this is s square plus 2s, then we can write this as minus 4 upon s square plus 2s plus 5, and we can write this as s square plus 2s plus 2. So this is square. So now this is the example. So now this is somehow critical example. So now to solve this example, that means we have to apply the partial fraction concept, because this denominator is not in our standard form. That's why we are applying the concept which is called as partial fraction. If we apply the partial fraction concept, then we can write this as s square plus 2s minus 4 divided by, this is s square plus 2s plus 5, then this is s square plus 2s plus 2. So just write down this equation in this way. So observe that, so these factors are quadratic and non-repeated. This is different, this is different. So factors are quadratic and non-repeated. So we can write its partial fraction as as plus b divided by first term, which is s square plus 2s plus 5, plus second factor is cs plus d divided by second term is s square plus 2s plus 2. So this is the second factor. So these are the quadratic factor. That's why we write the partial fraction rule for the quadratic non-repeated factor. Now our aim is to find out the value of a, b, c and d, which are constant. So now if we take denominator of this left hand side to the right side, we get this as s square plus 2s minus 4 is equal to, this is as plus b, this is the first term, into, after taking this side to right side, so this term will get cancelled and we get this as s square plus 2s plus 2. One term will get cancelled, plus this is cs plus d, then again after taking this side to this right side, one term will get cancelled and we get this as s square plus 2s plus 5. Now here our aim is to find out the value of constant a, b, c, d, but it is not possible here to find out the value of constant a, b, c, d by substituting or by putting particular value for the parameter s. So now in this case, expand right hand side of this equation. So we can write this as, so take the multiplication of these two terms, we can write this as a s cube plus 2a s square plus 2as. After multiplying as to the second bracket, now multiply b to the second bracket, we get this as b s square plus 2bs plus 2b. So after multiplication of this two term, we get such type of equation. Then plus take the multiplication of this term, we get this as c s cube plus 2c s square plus 5c s plus multiply this d to this term, we get this as d s square plus 2ds plus 5d. Now according to our method, arrange this equation according to the decreasing power of s. So highest power of s in this equation is s cube. So we can write this as s cube into coefficient of s cube is, this is a, then s cube coefficient, so this is plus c. This is the second coefficient. So now write down all the coefficient of s square term. So coefficient of s square term is 2a, then this is plus b, then we get this as plus 2c plus d. So these are the coefficient of s square term. Then write down the coefficient of s term. So coefficient of s term is this is 2a, so this coefficient is 2a, then next coefficient is plus 2b, then next coefficient is plus 5c, so this is the next coefficient, then plus 2d. So in this way we get the coefficient of parameter s. Now collect all constant term together. So now constant terms are, so here constant terms are 2b, so this is the first constant term. Now here we get constant term as plus 5d. So now in this way we can expand this right hand side and write this according to the decreasing power of s. So now here we get this as s square plus 2s minus 4. Now compare the like power term coefficient from both sides. We get this equation as 0 is equal to, so cube term is absent, so that's why 0. So this is a plus c. Now this is the first equation we are getting here. So now coefficient of s square is 2a plus b plus 2c plus d. So this is the coefficient of s square. Coefficient of s square on the left side is 1. So now next coefficient of s is 2, which is equal to, so this is 2a plus 2b plus 5c plus 2d. So let's call this as equation number 2. Let's call this as equation number 3. Now constant, so minus 4 is equal to, so minus 4 is equal to, so this constant term is 2b plus 5d. So now here observe that, so we are not getting any constant term directly from solving this equation. That means after comparing the left and right hand side coefficient, it is not possible for us to get direct value for the constant. So let's call this as equation number 4. Now here question is that how to find the value of such type of constant, because no one equation is same. So whenever such type of situation appear, then we can take the help of one equation to find the value of other equation. Now here friends, if we observe the first equation, so then we cannot compare this first equation with second, third and fourth equation. We cannot evaluate this equation in simple way. So if we write the value of a is equal to minus c, so from this first equation, so that means from equation 1, so we get the value of a is equal to minus c, or we may put this as a is c is equal to minus a. In both way it is possible. So now put a is equal to minus c in equation 2 and 3. So now if we put in equation 2 and 3, so after putting this value in equation 2 and 3, we get this equation as 1 is equal to, so this is 2a, so we can write this as, so minus so we can write this as minus 2c plus b plus 2c plus d. So that these two terms will get cancelled, and finally we will reach to the term 1 is equal to, this is b plus d. So let's call this as equation number 5. Now here also we are not getting the answer to any constant. So now put the value a is equal to minus c in equation 3. So in equation 3, if we put this value, then we get this as 2 is equal to minus 2c plus 2b plus 5c plus 2d. So after putting the value of a is equal to minus c, we get this as minus 2c. So remaining terms as it is. So now here if we try to simplify this equation, then we get next step as 2 is equal to, so this is minus 2c and this is 5c. So we can write this as 2b plus 3c. So 2b plus 3c plus 2d. So let's call this as equation number 6. Now here also we are not getting the value of any constant term. So but observe that, so this equation, so in this equation number 5 we get two constant b and d. Again in equation 4 also there are two constant which is b and d. That means if we solve this equation 5 and 4 simultaneously, then we will get the value of constant b and d. So this is one of the critical example. So now if we try to solve equation number 5 and 4 from equation 4 and 5. So what is the equation number 4? We can write this as minus 4 is equal to 2b plus 5d. So now to cancel one term, so we are interested here to solve this simultaneously. So now to cancel this term, we can write this as 1 is equal to b plus d. Now to cancel one variable, so multiply this equation by 2. So after multiplying this equation by 2, we get this as minus 4 is equal to 2b plus 5d. Then this is again 2 is equal to 2b plus 2d. So take the subtraction of this term. So change the sign while subtracting this term. So we get this as minus 6 is equal to, so this term will get cancelled. So then we get this as 3d. So we get this as 3d. So from this equation straightforward we get the value of d as, so this is 5, then this is plus 3d. So we get the value of d as 3 to the 6, so minus 2. So we get the value of d is equal to minus 2. So now put d is equal to minus 2 in any one of this equation. So either put in this equation or in this equation. So we get this as 1 is equal to, this is b plus d. So we directly get the value of b is equal to, so we get this as b is equal to 1 and this is 2. That means value of b is 3. So this is the way where we get the value of second constant b is equal to 3. So now we get the value of two term b and d. Now next thing is that, so find the value of a and c. Again question arises that how to find the value of a and c. So we cannot get the value of a and c from this first this 5 equation, 4 equation. So but if we observe this equation number 6, then in this equation number 6 we get this as 2 is equal to 2b plus 3c plus 2d. So this is from equation 6. So in this equation we know the value of b, we know the value of d. So we get the value of constant c from this equation number 6. So we can write this as 2 is equal to, so I will just clear this term. So we get this value as 2 is equal to, now 2 is equal to 2 into b, which is 3. So we get this as 3 to the 6 plus 3c plus 2 into 2, 4. So we get this as minus 4. So we can get this as minus 4. So that we get this as 2 is equal to 2 plus 3c. Then we get the value of this term as 2 minus 2 is 0. So finally we will reach to the answer of c as 0. So because after taking 2 to this side, so we get 2 minus 2 0. So 0 upon 3 means this is 0. So we get a third constant value c as 0. Now we know that A is equal to minus C. So if C is equal to 0, so this indicates that A is also equal to 0. So friends, this is totally new concept for finding the value of partial fraction. I hope you understand this method, which is somehow complicated. Now put the value of constant A, B, C and D in equation number 1. So let's call this as equation A. So put all this value in this equation number A. So substitute in equation A. So put all this value in equation A. So that after putting this value in equation A, we get this equation as, so which is equal to A is 0, which is 0s plus B. B is 3. So we can write this as 3 divided by s square plus 2s plus 5. Then plus put the value of C. Value of C is 0. So we can write this as 0s plus D. So value of D is minus 2. So we can directly write this as minus 2 upon this is s square plus 2s plus 2. So after putting the value of constant in this equation A, we get new equation. So which is the equation which we obtain after partial fraction. Now after obtaining the partial fraction, observe that we can take the inverse Laplace transformation on both sides. So we can write this as by inverse Laplace transformation. So if we apply the inverse Laplace transformation, then we get this as inverse Laplace transformation of s square plus 2s minus 4 divided by this is s square plus 2s plus 5 first term, then second term is s square plus 2s plus 2. Now this is the inverse Laplace transformation to the left side. Similarly, take the inverse Laplace transformation to the right side. So we can write after simplifying this term as 3 divided by s square plus 2s plus 5. Then here middle sign is minus. So this is 2 upon s square plus 2s plus 2. So after taking inverse Laplace transformation to right and left side, we get this type of equation. Now apply the linearity property so that we can get the next step as, so this 3 is constant, so outside the inverse Laplace transformation. So inverse Laplace transformation of 1 upon this is s square plus 2s plus 5. Then this is minus 2 into inverse Laplace transformation of 1 upon s square plus 2s plus 2. Now friends, here observe that, so we get inverse Laplace transformation for this two term, but observe that neither this equation or this equation is in our standard form. So even though we do the partial fraction of this term, so this equation is not in our standard form. So let's do some adjustment so that we can easily convert this equation in the standard form. So now here adjustment is required for finding the inverse Laplace transformation of this term. So now here observe that first term is s square and second term is 2s. So if we make the square of s plus 1, it's square. So we can write this as s square plus 2s. Then plus 1 is there. So actually we get here s square plus 2s, which is s square plus 2s. So we require here 5, we get here 1. So let's take this as 4. So that we can take next term as inverse Laplace transformation of 1 upon this is s plus 1. So we can write this as s plus 1 its square plus 4. So we can write this 4 as 2 square, so that we can apply any one of this concept. So now here we can write this as minus 2 into inverse Laplace transformation of 1 upon. So here again, so first two terms are same, which is s square plus 2s. So we can write this as s plus 1 its square. But here so this last term, so last term is plus 2. So now here we get 1, so we require one more term. So for this one more term, so write down this as 1 square. So that after making square of this term, we get this denominator term as it is. So after taking square and simplifying this equation, we get this denominator term as it is. Now here, observe that we can apply the concept of second shifting theorem, so which we already learned under method number 2. So for detailed information about method number 2 for finding the inverse Laplace transformation by second shifting theorem, so please watch our previous video lecture. Now according to the second shifting theorem for inverse Laplace transformation, we can write this as, so here constant a is added to the parameter s, so we can write this as e raised to minus t into, this is inverse Laplace transformation of 1 upon s square plus 2 square, this is minus 2, again 1 is added to the parameter s, we can write this as e raised to minus t into inverse Laplace transformation of 1 upon s square plus 1 square. So now once again simplify this, we get this as 3 e raised to minus t, then this is the standard result, number 4, 1 upon s square plus a square, which is 1 upon a sine of at, where value of a is 2, so we can write this as 1 upon 2 into sine of 2t minus 2 e raised to minus t as it is. So now once again this equation is in standard form number 4, where the value of a is 1, so we can write this as 1 upon 1 into sine of 1t, that means sine of t. So friends, this is one of the critical example which we solve with the help of partial fraction. So after taking partial fraction, again such type of adjustment is required for solving such type of example. So now friends, this is one of the method for solving such type of example. So there is one alternative method also available for solving such type of example. So this is the first method for solving example. Now we will discuss the second alternative and simple method for solving such type of example. So for solving this example by second method, we will take the same example. So we are discussing second method with the help of same example. So now let's try to understand that. So in previous method, we directly apply the concept of partial fraction for quadratic term. Now here, we are applying substitution concept for obtaining the partial fraction of the equation. So now this is the simple method, but this method is alternative method to the current method. So now here observe that, so this term s square plus 2s, s square plus 2s is common for both the term in the denominator. So in particular, if we put s square plus 2s is equal to t. So let's assume that this as parameter t. Then we can write given equation as s square plus 2s minus 4 divided by, this is s square plus 2s plus 5 into s square plus 2s plus 2. So we can write this equation after putting s square plus 2s is equal to t. So in numerator we get this as t minus 4 divided by, so for this two term we can write this as t plus 5. Again for this two term we can write this as t plus 2. Now friends, observe that, so because of this substitution we get simple term. So now this is first term and this is second term. So here power of t is 1 and these factors are linear and non-repeated. So according to the partial fraction rule, we can write this as a upon t plus 5 plus b upon t plus 2. Let's call this as equation number 1. So after substituting this value, we get such type of simple equation. So this is the alternative method to the same example. So let's discuss this method. So now we can write this as t minus 4 is equal to a into t plus 2 plus b into t plus 5. So now find the value of constant a and b. So to find the value of constant a, put t is equal to minus 5. So after putting t is equal to minus 5, this term becomes 0. So we get this as minus 5 minus 4. This is minus 9, which is equal to, so this is minus 5. So we get this as minus 3a. So we get the value of a is equal to, so we get the value of a is equal to 3 3s are 9. So we get value of a is equal to 3. So now this is the first term, which is the first constant. Now to find out the second constant term, so to find the value of b, put t is equal to minus 2. So now this become minus 6. So then we get this equation as this is 0. So then this is minus 2 and this is again 3b. So now we get the value of b is equal to minus 2. So b is equal to minus 2. Now here we get the value of constant a and b. Put this value in the first equation. So we get this equation as so we can write this value of a is equal to 3 and b is equal to minus 2. So after putting the value of constant, we get such type of equation. Now friends, let's take the inverse Laplace transformation to both sides. So after applying inverse Laplace transformation to both sides, we get this as inverse Laplace transformation of s square plus 2s minus 4 divided by, this is s square plus 2s plus 5, then this is s square plus 2s plus 2, its inverse Laplace transformation left side. So which is equal to inverse Laplace transformation of, this is 3 upon t plus 5 minus 2 upon t plus 2. Now apply the linearity property. So we can write this as 3 into inverse Laplace transformation of 1 upon t plus 5. So first term minus 2 into inverse Laplace transformation of 1 upon t plus 2. So now friends, observe that, so in original equation we get the parameter s. Now here we get the parameter t for finding the inverse Laplace transformation. So once again re-put the value of t, so that we get this as 3 into inverse Laplace transformation of 1 upon. So what is the value of t? So t is equal to s square plus 2s. So we can write this as s square plus 2s plus 5. So we get original equation as it is, minus 2 into inverse Laplace transformation of 1 upon, put the value of t here again. So we get this as s square plus 2s plus 2. So now our aim is to find out the inverse Laplace transformation of this first term and second term. But observe that, so this first as well as second term is not in our standard form. So our first aim is to convert this denominator in terms of standard form. So now let's do some adjustment so that we can get the standard form of this equation. So once again, if we observe the first two terms of this equation, then this is the square of s plus 1, its square. So its square is s square plus 2s. Then plus 1 is there, but we require here this term as 5. So we can write this as plus 4. So next step is 3 into inverse Laplace transformation of 1 upon, this is s plus 1, its square plus 4. So we can write 4 as 2 square because we require the value of a square for applying the standard result. Here square is available. Now we can write this as 2 into inverse Laplace transformation of 1 upon. So now for the second term, so same concept is there. So we can write this as s plus 1 its square. But here we require, so after simplifying this term, we get this as x square plus 2s plus 1. But here we require this as 2. So we can write this as plus 1. So we can get this as 1 square. Now apply the concept of second shifting theorem for inverse Laplace transformation. So for detail, please watch our previous video. So we get this as 3 into e raised to minus t into inverse Laplace transformation of 1 upon s square plus 2 square minus 2 into e raised to minus t into inverse Laplace transformation of 1 upon this is s square plus 1 square. Now this equation as well as this equation is straightforward in our result number 4. So we can directly write the answer to this term as e raised to minus t. Then after applying this result number 4, we get this as 1 upon 2 sine of 2t minus 2 e raised to minus t into this is sine of t, because value of a is 1. So now friends, observe that we solve the same example with the help of two different methods. So in first method we directly apply the concept of partial fraction for quadratic factor which are non-repeated, but here so we apply the concept of substitution. That means we can solve the same example with the help of two different methods. Now here question arises that which is the correct method. So friends, both methods are correct. So if you understand the first method and if you feel that first method is simple, then you can apply the first method. So if some people feel that this second method is simple for them, so you may apply this second method. But if we apply first method or second method, you will reach to the same answer. So even though if you apply first method or second method, you will get the same answer finally for such type of example. So friends, this is the second example we discussed, which is critical and based on the inverse Laplace transformation by partial fraction. Now let's take one more example to understand this concept clearly. So now take the third example. So example 3. Now friends, let's discuss the third example, which is somehow critical. So after understanding this example, your idea for finding the inverse Laplace transformation by partial fraction will get clear. Now example is evaluate the inverse Laplace transformation of this is s upon s square plus 4 and this is s square plus 9. So these are the two terms. So now here we may put s square is equal to t and we get the linear and non-repeated factor, or we may solve this equation with the help of quadratic factor. So if we try to write the quadratic factor, then we get this as as plus b upon this is s square plus 4 plus this is cs plus d upon s square plus 9. So if we simplify this, then we get this as s is equal to as plus b, then this is s square plus 9 plus this is cs plus d, and we can write this as s square plus 4. So this is the straightforward and direct method for finding the partial fraction of such type of term where denominator is in terms of quadratic form. So now just simplify this term. So we get this as a s cube plus 9as plus b s square plus 9b, then we get this as c s cube plus 4cs plus ds square plus 4d. So after taking the product of this term and this term, we get such type of expansion. So now arrange this equation according to the decreasing power of s. So highest power of s is s cube, so we can write the coefficient of s cube as a, then next coefficient is c, plus arrange all the coefficient of s square, collect all the coefficient of s square. So s square term is b, then this is plus d, plus all coefficient of s, so s term is 9a, then we get this as plus 4c, then all constant term together, so constant term is 9b, this is 9b plus 4d. So now friends, this side is only s, so here s cube coefficient is 0, so we can write this as 0 is equal to a plus c. So now here again s square term is absent on the left side, so we can write this as 0 is equal to b plus d. Then value of this s is 1, so we can write coefficient as 1 is equal to 9a plus 4c. So then again we get this as 0 is equal to 9b plus 4d. So now again here question is to solve this equation with the help of simultaneous equation. So now here we are not getting the straightforward answer, but observe that. So this is our first equation, this is second, this is third equation, and this is fourth equation. So friends, observe that. So first and third equation, so terms are a and c, here also term a and c. So if we try to solve these two equations, first and third simultaneously, then we get this as 1 is equal to 9a plus 4c. So now to cancel a term, so multiply this equation by 9, we get this as 0 is equal to 9a plus 9c. So after multiplying by 9 to this first equation to solve simultaneously. Now change the sign of this equation. So this term will get cancelled. So here we get this as 1, then which is equal to, this is minus 5c. So that after calculating the value of c, we get this as minus 1 upon 5. So this is the value of first constant. So c is equal to minus 1 upon 5. If we put this value in this equation, then we get the value of a is equal to 1 upon 5. So in this way we get the value of two constant a and c. Now question is to find out the value of b and d. So observe the equation number 2 and 4. 2 and 4. So here equation 2 and 4. So this fourth equation is 0 is equal to 9b plus 4d. So now to cancel b term, so multiply this equation 2 by 9, or if we wish to cancel the d term, then multiply this equation number 2 by 4. Suppose we will cancel here a d term. So multiply this by 4, we get this as 0 is equal to 4b plus 4d. So now change the sign. So after changing sign, we get this as 0 is equal to 5b. This term will get cancelled. So that means we get the value of b is equal to 0. So once if we get the value of b is equal to 0, so from this equation it is always possible for us to calculate the value of d. Again from this equation second, we get the value of d also equal to 0, because b is equal to 0, so this directly d is equal to 0. So here we get the value of all constant term a, b, c and d. Now put all this value in this equation. So let's call this as equation number a. So substitute in equation a. So put all this value in equation number a. So after putting this value in equation a, we get next step as so let's put this value. So after putting this value, we get next step as which is equal to a, which is 1 upon 5s plus b, which is 0, divided by s square plus 4 plus c, which is minus 1 upon 5s plus d, value of d is 0, divided by this is s square plus 9. So now we get two term after partial fraction. Now apply the concept which is called as inverse Laplace transformation. So by inverse Laplace transformation we get next step as, just clear me this board. So now if we apply the inverse Laplace transformation, then we get this as s upon s square plus 4 s square plus 9, its inverse Laplace transformation, which is equal to inverse Laplace transformation of 1 upon 5s divided by s square plus 4 minus 1 upon 5 inverse Laplace transformation of s upon s square plus 9. So in this way we get the next step. So now here apply the concept. After applying the linearity property, we write this step directly. So take 1 upon 5 constant outside the inverse Laplace transformation, we get this as s upon s square plus 4 minus 1 upon 5 into inverse Laplace transformation of This is s upon s square plus 9. So friends, observe that this first equation is directly in our standard form number 6, s upon s square plus a square, where the value of a is 2, 2 square is 4, so which is cos of 80. So we can write this as 1 upon 5 into cos of 2t, then again minus 1 upon 5 as it is. So same result is applicable here, but value of a is 3, so we can write this as cos of 3t. So after taking 1 upon 5 common, we get this as cos of 2t minus cos of 3t. So here friends, we solve only 3 examples, but all these 3 examples are critical and which is based on the third method for finding the partial inverse Laplace transformation by partial fraction. So now for your practice purpose, let's take some examples. Now friends, time is to test your knowledge. So for your practice purpose, only 3 examples are given. This is first, second and third example. So apply the concept of partial fraction. So for applying concept of partial fraction, we may directly apply the concept of partial fraction for a quadratic term, or we may put the value of s square plus 2s as t, or s square plus 2s s square plus 4s as t, and then after substitution it is always possible for us to find out the partial fraction and its inverse Laplace transformation. So try to solve by both method, and in examination apply the method which is convenient for you. So please solve these 3 examples. So along with these 3 examples, answers are provided. Friends, I hope you people like this lecture. So thanks to one and all. Thank you.